welcome to the new talk series by the Math Club. So the idea behind this talk series is to introduce people to the world of maths research. So a lot of us are like fresh out of school, and we have very little idea of what research in math is. Like the courses at IISER sort of give us a flavor of what research is, but they're mainly the finished product of research, and we don't see the research in progress. So the idea behind this talk series is to get mathematicians who are actively working in these fields to present a thing or two about their field. So yeah, with that, I'll hand it over to the speaker, Professor A. Raghuram. He works on the Langlands program, and today he'll be talking about what is number theory.
Thank you for this introduction. It's a very good idea that you're starting this series. So somehow the job is to give you an idea of what is research about. I don't know if I'm really so qualified. I mean, okay, I don't suffer from false modesty. So I am a researcher, but then you go to a important center for mathematics, like the Institute for Advanced Study, and then you see people like Deline, and then you wonder, what am I doing, kind of thing. But nevertheless, I have something for all you guys. Let me just write it out. Die Mathematik ist die Königin der Wissenschaften und die Zahlentheorie ist die Königin der Mathematik. You can guess what this might mean. Anyone? Mathematics is the queen of the sciences, and number theory is the queen of mathematics. Who said this? Carl Friedrich Gauss, or just Carl Gauss. I have one more. Die ganzen Zahlen hat der liebe Gott gemacht. Alles andere ist Menschenwerk. Can you guess what the sentence means? One of you just. Die ganzen Zahlen is a set of all numbers, literally, I mean integers, is the work of the dear God, and everything else is man's work. Who is this quote usually attributed to? You can't hear me. I can hear myself very clearly. Okay, we start again. Die Mathematik is the... No. So the garden... Okay, so this is... Whose quote is? Kronecker. What was his first name? Leopold. Anyway, this is just to kind of... for me to warm up and for you to warm up. So I have given a title. I was going to say a pompous title, but the pomposity or being pompous is forced upon me by the series itself. What is something? What is number theory? You see, any such thing, it's very vast. You have to understand, I can be at a conference on number theory, and a fellow number theorist, so I fancy myself a number theorist now, and a fellow number theorist might be there, and we might have nothing to talk to each other other than, the beer was good, or this is good, or whatever, It's a very vast, I suppose any one particular, any subject it's in the nature of human knowledge, I suppose, the vastness. Anyway, so I will weave some storyline about number theory, and hopefully you get something out of it. Okay, I wanted to have some idea. I see some PhD students who I'm familiar with. Do we have first year BSMS students here? Oh, very good. Let's move on. Second year. All right. So you see, this is very good that you guys are here, and hopefully at least one of you will go back home feeling a little inspired. Anyway, so what I was going to say was I start with an apology that one is constrained by this language of mathematics. You see, you've just come out of school, you're kind of in some seemingly fancy place, and it takes a while to, if I start talking about, take a cuspidal automorphic representation, it means nothing at all to most, and probably not much to me either. So there's this whole business, there's a lot of language. It's, mathematics is the language of the sciences, as Galileo had once famously said. So I'm constrained by the fact that, many of us in this room are unfamiliar with the language of higher mathematics. So at the level of basics, I still want to, trigger some thoughts. Anyway, with that apologies, let me just get started. Of course, as Kronecker said, God made the numbers and everything else is the work of man. We start with natural numbers, n, which is the set of all these positive integers, and this is Bourbaki notation, 0 is included there. Go look up Bourbaki, Nicholas Bourbaki. And then, well, you can't live your life here, even if you wanted to do some bartering, you need negative integers, and one often denotes that by z. The first letter of the German word for number is z, and this is all integers. So what is number theory? Number theory is the study of this set. I'm done, let's get dinner. Okay, so we get started here, and then, all of you would have certainly seen what's called the fundamental theorem of arithmetic. Which is the statement that every integer, I might just say positive integer, take a number like 6, I can somehow pull it apart as 2 times 3, but 2 and 3 itself, I can't further factorize it in terms of integers. So every positive integer is, and the only way 6 I can write as indecomposable integers, which is called a prime, and that's unique. It's 6 is 2 times 3. So more generally, every positive integer is uniquely a product of primes. So let's start here. I've used a word prime, which I know is done in high school mathematics. So what's prime? Prime is a positive integer is said to be a prime if its only divisors are 1 and itself. And then you know that the primes are 2, 3, 5, 7, 9, 11, 13, 15, 17, and so on. Yeah? Typical maths day thing is, you mug up the first so many primes, and there used to be a prime number b in our mathematics day, and if you have learned the first 200 primes, you might actually go back home with $500 or something. So in any case, I've already fudged a little. I've just put a ... And the question is, well, does this set kind of finish up somewhere or not? And this is probably the first major theorem in number theory. This is a theorem going back to Euclid. What is this theorem I'm going to put down? there are infinitely many primes. And I think everyone should know a proof of Euclid's theorem. Euclid's theorem will justify my ... here. So what's the proof? This is the first, one of the most famous proof by contradiction. I'm sure many of you know this. Suppose not. Suppose there were finitely many primes. Call them something, P1, P2 through P something, Pn. I don't want to put commas, but suppose this is all the primes. Then you consider an integer n, which is the product of these guys, and you add 1. So this is a positive integer. Either it's a prime itself or not. And if it's a prime, in any case, there is a prime which divides it. And that prime needs to be, since this is a set of all primes, it's got to be one of these pi's. But then it divides n, it divides, if it's pi, it divides the first summand. Therefore, it divides n minus this. In other words, it divides 1. But 1 has no prime divisor. Okay, none of these guys are going to divide 1. So you kind of dig yourself into the hole by the supposition that there were only finitely many primes. In other words, so that assumption is wrong. This is the proof by contradiction. So the essence is just this construction. Let me consider this. You can fill it out. Okay, I'm not giving a course here. Just the essence of the proof. Let me do some other proofs. So this very likely, don't feel embarrassed. How many of you have seen this proof? Okay, so I like to say almost all. Okay, so let me just play around with Euclid. So this is proof number 1. Consider, so again, it's it's almost like a proof by contradiction. It goes slightly differently. So suppose P1 through P, let me say L of n, are all the primes less than or equal to some integer n. Okay, and consider now this quantity lambda n. Lambda n is the product of I going from 1 to this L of n of 1 minus 1 over pi inverse. Okay, consider this. What kind of quantity is this? Well, you have done your geometric expansions. One over 1 minus x, if x is small, you can write this as 1 plus x squared plus ... x to the n plus ... This is an exercise. I can do this. This inverse is really 1 over 1 minus. So if I were to take x as 1 over a prime, this looks like 1 minus 1 over p. This guy inverse looks like 1 plus p squared plus all powers of. So this n is not that n. Maybe I'll make this a k. 1 over p to the k plus ... So what does this finite product represent? So every factor captures the sum of reciprocals of all that particular p power. If I multiply this together, then this would be, it's going to look like a sum of terms p1 to the sum. Maybe it picks up the a1's term there. So p1 to the a1 through pk to the ln to the a ln, where the summation is over all tuples, ln tuples of non-negative integers ai's. Now if I appeal to the fundamental theorem of arithmetic, what is this capturing? So this n is itself a prime, or is a product of primes, and the possible products, the primes will have to be smaller than n, so it's amongst this set. So this is really, well, it's at least 1 over, it's at least summation 1 over, give me some other letter, m going from 1 to n. Take any integer less than n, m, I look at 1 over m, look at its prime factors, it's amongst these, so that should appear here. And this might have more terms. So this term is at least this much. And what do I know about this guy? This you have seen in your calculus courses. You know that, so now if I take limit as n goes to infinity, I know this diverges. I know that this diverges. Yeah, so you've seen this as the harmonic series, maybe summation 1 over m diverges. M going from 1 to infinity. This, by the way, is a 14th century theorem. I don't know how many of you know this. There's a nice math trivia. Anyone knows who proved this? It's a 14th century theorem. Math club people, you should have a math trivia quiz. This was proved by a French philosopher, Nicole Theorem. I'm not sure about the accent. In any case, this diverges. So now this gives me a proof that there are infinitely many primes, because suppose not, if there were only finitely many and maybe they were all less than something, then this term here cannot be shooting off to infinity. It's a finite product, it's finite, it converges. Yeah. Third proof, which kind of pushes this a little further, which I won't do, but I'll leave this as an exercise. It's somewhat like this, the divergence of this harmonic series. Prove that summation 1 over p as p runs through all primes diverges. Anyone knows the proof of this? Now the floor is open to the PhD students. Aha, very good. Give me a proof. Go ahead. Do you know a proof of this? Yeah. Okay, tell me.
We have to take generally we have to write the sum 1 by 1 plus 1 by 2 plus 1 by 3 and so on, and where is greater than or equal to 1 plus 1 by 2 plus 1 by 2 plus 1 by 4 plus 1 by 4 plus 1 by 4.
You're talking of the divergence of this series. So here I'm running over only primes. That argument is not going to work. Your proof is actually what you just gave. That's fine, you missed it. That is in fact Theorem's proof. That is the 14th century. This was the original proof of divergence of this. This one you won't be able to club together the first 2 terms, the next 4 terms, the next 8 terms, and so on. It's a little subtler. Has anyone seen a proof of this? So actually, I will be honest with you. I also knew a proof and I forgot. And while I was preparing this talk, I was like, okay, this is a cool statement. I know it's a non-trivial exercise. And I reminded myself how it goes. You can look this up in Ireland and Rosen. The book is called A Classical Introduction to Modern Number Theory. Many times I get emails by someone or the other in typically first year, second year, third year zone, who will email or come to my office asking what to read. And my standard answer is go read Ireland and Rosen's book if you wanted to read number theory to get started. Okay. Somehow in our IISER curriculum, we don't kind of chew on basic number theory. There's only a course on algebraic number theory, which might change in the near future, but you guys may not see it. Okay, anyway, this is a wonderful book. All right, so we have infinitely many primes, and I was almost going to say there are infinitely many proofs. Here is true. Now, I want to play around with this idea of infinitude of primes, slightly focusing my attention on, well, I got this list of primes. Of course, this guy is an aberration. So you just forget that. All the others are odd numbers. If I take any odd number, 2n plus 1, depending upon whether that n itself is even or odd, you know that any odd number is of the form either 4k plus 1 or 4k plus 3. If I take an odd number and divide by 4, if I take any number and divide by 4, the possible remainders are 0, 1, 2, 3. 0 or 2 will force the guy to be even, and 1 and 3 is odd. Now let me tweak Euclid a little. I'll maybe just call this a proposition. Maybe let's elevate it to a theorem. So first statement, there exists infinitely many primes of the form 4k plus 1, and secondly, there exists infinitely many primes of the form 4k plus 3. These are typical exercises in a first course in elementary number theory. So I'm going to do this exercise for you. Let me start with the easier one. I want to prove there are infinitely many primes of the form 4k plus 3. The proof are all modeled on Euclid. Suppose not, you cook up some integer which will have a prime divisor, and then if you have cooked this up cleverly, here the cleverness was taking the product and adding 1. You do something like this, and you follow your nose, and out will pop another prime which is necessarily of a certain type, which can't be in this set. Okay, so that's the nature of the proof in either of these two cases. So let me do this here. So suppose P1 through Pn, this is all primes of the form 4k plus 3. I'll do that, the easier one first. And then anyone who's had some basic number theory, can you tell me what will I write down? Sorry, did I hear a Jordan holder? Yeah, okay, I take the product. And then? Let me look at this. Okay. So it's some artifice of this kind. So suppose this is all the set of all primes of the form 4k plus 3. Consider this integer. This has got to have a prime divisor. This guy, upon dividing by 4, also has a divisor, remainder 3. If all the primes dividing this were not of this type, then they're all of 4k plus 1, but two numbers of the form 4k plus 1 the product of two such numbers is again of the form 4k plus 1. If two numbers leave a remainder of 1 upon dividing by 4, the product will also leave the same remainder 1. So this guy not leaving a remainder 1 necessarily has a prime of the form 4k plus 3. So it's to be one of these. Therefore, that prime divides this, it divides minus 1. That's not possible. So somehow this is the key point. Yeah, you can fill out the proofs. Already by a few blank looks, I can tell that some of you weren't with me, but that's okay. It's stare at this and figure it out. It's not hard. Let me do a slightly harder one, 4k plus 1. So I want to prove there are infinitely many primes of the form 4k plus 1. For this, I want a sub-theorem. Just so that you go back home having actually learned some number theory here. Here is I'm using this in the aid of a proof of a theorem, let's call this a lemma, but this is a theorem in its own right. So P is a prime. P is always a prime in number theory. Let P be an odd prime. If the equation x squared congruent to minus 1 mod P has a solution. So this is, by the way, this notation is due to Gauss. He should go and look up somewhere his meditation over notions versus notations, and somehow having a good notation aids a lot in mathematical thought. That rhymed well, it aids a lot. Anyway, so this means I'm trying to find integers whose square is minus 1 modulo P. In other words, after dividing by P, it leaves a remainder minus 1. This notation A is congruent to B mod something means the difference is divisible by that modulus. So I'm trying to find square root of minus 1 modulo a prime. this has a solution in integers implies this prime p is of the form 1 mod 4. This is due to Euler. By the way, so when you come out of school, many people in school pronounce this as Euler. It's Euler. Euler came out of the German-speaking part of Switzerland, and EU in German is Eu. But Euclid is Euclid and not Euclid. Euclid didn't come out of any German-speaking part of any. Where did Euclid come out of? So anyway, proof of this. So suppose there is some integer which, suppose I have some integer which pretends to be like the square root of -1. What you do is you raise both sides. P is an odd prime, so I raise both sides to the p minus 1 by 2th power, which is an integer, p being odd. And this side is a to the p minus 1, and that's congruent to -1. And there is what's called Fermat's little theorem, which says that if I have an integer a not divisible by p, then its p minus 1th power itself is congruent to 1. This is congruent to 1. So I get -1 to the p minus 1 by 2 is in fact 1. That congruence actually becomes an equality. Think about that step a little. And this will imply that, well, p has to be of the form 1 modulo 4. If p is like the number 3, then 3 minus 1 by 2, this becomes odd, so -1, that becomes -1 left-hand side if p is 3 mod 4. So there are this kind of, any number of this type of congruence properties capturing something about the shape of the prime. And Gauss's greatest achievement, one of his greatest achievements, at least in number theory's greatest achievement, is what's called quadratic reciprocity. He was so fond of that theorem that he gave several proofs in his lifetime. Captures statements like this. So this gives you a handle on some primes of the form 4k plus 1. And now we go back here. Suppose now these were all the primes of the form 4k plus 1. Your ingenuity is cooking up an integer n, which somehow includes all these primes. Give me the integer. I've done some exercise for you in some sense. Say this again. It's okay. At worst, you're wrong. That's right. I take the product of all these guys, square it up, and add 1. I don't know. Did you say the square or not? Yeah. So suppose these are all the primes of the form 4k plus 1. Consider an integer like this. Why is this going to work? Because of, well, there is some theory which says that I can identify primes of form 4k plus 1 through some such gimmick. So if a p divides this n, well, then this guy, this product of numbers p1 through pn, is a solution of this equation. If p divides this, that's to say, well, this little a is this. So this p is of the form 4k plus 1. It has to be one of these. It divides this. It divides this. So it divides 1. Contradiction. The rest of the proof is really formally it looks the same. So the only, well, Euclid is gone there. The only thing was to cook up the right sort of integer. As you can imagine, already for 4k plus 1, this was not totally trivial. Okay, I mean, I needed some. It's important. It's serious number theory, but it's, this is all well-known and 200-year-old mathematics. Suppose you ask yourself the question, are there infinitely many primes of the form 17k plus 5? Okay, then you're going to be really hard-pressed in coming up with some kind of criteria like this, which captures that sort of shape of that prime. So there is one wants to think about this in some systematic, some structural way. And now enters, so you see I've mentioned so far, what are all the names I've mentioned? But I already Gauss. Kronecker hasn't showed up in this, but Euclid. Euclid, Gauss, Fermat. By the way, it's Fermat, Euler. Anyone else? And now for the next one coming up is, before I mention that next name, you can ask questions. So of course the whole point of research, I have to say something about doing research. Okay, the whole point is to keep asking questions. You ask 10 questions, quite likely, but by you I don't mean you in particular. When one asks 10 questions, it's quite likely that, I don't know, 5 or 6 of them are just impossibly naive and stupid, which is certainly the case with me. Maybe there might be a hit here and there, meaning there's something reasonable. For example, here there are infinitely many primes of this type, infinitely many primes of this type. It's conceivable that this is a larger infinity. Now this has to be qualified. Now you know that of course everything is a subset of integers, and that's a countably infinite. Such words make sense? Countably infinite, uncountably infinite? Some of you are not, okay. So it's literally the same kind of infinity, but still in this, if I throw a prime at you at random, is the probability half, that it's of the form 4k plus 3, and probability half of the form 4k plus 1? Or is it so that maybe it's highly probable that it's 4k plus 1 and sort of less likely of the form 4k plus 3? You can ask this question, okay? And you kind of try to formalize this. So suppose, I don't usually do this in a maths talk, but it's okay. Suppose there is an entity that, let's just call this God. And this God throws, I mean, he's not relieving himself, he's throwing primes. He's throwing a lot of primes, other than the prime 2, which he keeps in his hand. He throws all the odd primes. And we humans are trying to collect them in two buckets that we label as 4k plus 1 and 4k plus 3. And you can formalize this question a little better. You know, will I, as they start filling up, suppose I go up to the million and ask myself, what is the fraction of primes here and of the total number of primes up to a million, and what fraction is here? And there's nothing special about million. So you go up till an integer n, take the set of all primes less than n. In that, ask how many landed here and how many landed here. So those fractions will give you some kind of probabilistic statement. And what do you think is the answer? How do you know? You know this. So of course, one just can say that I just have divine intuition and I just know that this is the case. So this is a deep theorem, that in fact half of the primes lie there and half will come here. This theorem is due to another great German number theorist of that era, Dirichlet. Lejeune Dirichlet. I want to talk about Dirichlet's theorem, but now I'm going to completely change tracks. I go back to another 14th century theorem, to which, as is very popular in the current milieu, we claim everything is, the ancients knew this, but in this case, there was a person by the name Madhava. It's not exactly clear what in particular Madhava did, but there was a Kerala school of mathematics in 14th century, and this goes back to Madhava. But in calculus books, given the Eurocentric development of knowledge, this statement is attributed to Leibniz, that if I take the alternating series of reciprocals of odd integers, positive integers, this first of all converges. That's easy. You would have seen this in your calculus courses. You can apply the alternating series test. Any series with alternating terms whose in value they go to 0, you can actually hand wave a proof for. I take 1, I subtract 1/3, so I'll come back, and then I add 1/5, so I don't go all the way. And then I subtract something, I add, subtract. You can kind of literally feel that it's kind of converging to something, and you can make a proof out of this hand wave. So this converges, that's easy. What it converges to is interesting, and that's, or maybe I should have asked you if you knew this, but anyway, it converges to pi by 4. Proof? Yeah, okay, so many of you are. So you look at tangent inverse of x, some people call it arc tan x, and you can look at this Maclaurin expansion in a neighborhood of 1. And then you put x equals 1, and then out pops tangent inverse 1 is pi by 4, and on the other side you get that series. This was actually Madhava's proof also, couched in Sanskrit verses, so no one understood till very recently. There is a person in IIT Bombay, Ram Subramaniam. So he is a bit of an expert. We have had him here give an institute colloquium. He talked about what Madhava and Kerala School of Mathematics actually knew, the Sanskrit verses, and how exactly it translates. And he gave a very interesting talk on the proof of this theorem. Actually, I seem to have completely changed tracks. I was talking about primes, infinitude of primes, then infinitude of primes of a certain type, and then I'm just throwing some other series here. And it's so this, I'm going to take this off. It's a great theorem in number theory, which in fact is considered by many as one of the starting points of analytic number theory, the theorem due to Dirichlet, which states that the fact that this series, well, I don't care so much about the pi by 4. The interesting thing is that this series adds up to something which is not 0. This innocuous looking statement implies, and this is the content of Dirichlet's theorem, it implies there exists infinitely many primes of the form 4k plus 1. There exists infinitely many primes of the form 4k plus 3. And in fact, and these are of equal densities, half-half. All of that is captured, follows from non-vanishing of this particular series. This is amazing. You sit down and just stare at it. What is this guy got to do with some of you are fond of doing these reading courses. This makes, I've given you one reference, Ireland and Rosen. Ireland and Rosen's book has a proof of this theorem. Another great reference is this book by Serre, or if you want to pretend that you know some French, which for me is, I'm certainly pretending I don't really know French, you have to say Jean-Pierre Serre, or Jean-Pierre Serre. Serre's book on course in arithmetic. Serre, I don't know, someone could correct me, he's probably the oldest living Fields medalist and Nobel laureate. He's in his 90s. Atiyah has passed away, so Serre probably, he's in his 90s, I know this for sure. Serre and Tate were, by the way, I mean, many of you, I don't know how many of you know, one of the greatest number theorists of our times passed away a few days ago, John Tate. Tate and Serre were contemporaries. Anyway, so back to this. So this is another reference for this theorem. So I want to talk a little about the kind of philosophical content of this sort of a, how does this relate to primes of the form 4k plus 1 and 4k plus 3? So I'll give you a little bit of what Dirichlet did. I can't give you a proof of this theorem. Yeah, what I was going to say was, this makes a fantastic one semester reading project. You can just read this by yourselves. In fact, when I was a student in IIT Kanpur, the first course in analytic number theory was starting from scratch and ending with a proof of this theorem, literally. And this was one of the references. There's also a book by Apostle called Introduction to Analytic Number Theory, and that also has. But really, my favorite, and in fact favorites of many, is this book by Ireland and Rosen. It's, those of you who want to read some number theory, just spend the next summer or whatever. Just read through that book. Okay, so let me give you a hint of what Dirichlet really did. So you take an integer n, and you look at residue classes modulo n. So this is notation for all integers. When I divide, all the possible remainders I get upon dividing by n. There is some structure to this. I can add and multiply. It's called a ring. I can look at those which are relatively prime to n in the set. So I look at those A whose GCD with n is 1. This forms a group. There is some idea of taking an inverse. I can take n is 7, take the number 2. What is the inverse of 2? 3, 4? 4, yeah. So 2 times 4. So I can invert the number 2. If I just work with integers relatively prime to 7, 2 times 4 is 1. It's as if 4 is like 1 over 2. So there is some structure to this. And you take a map from this to non-zero complex numbers. For those of you who know such words, take a homomorphism of this group. And then you inflate this to a function, which I'll also denote chi, on natural numbers to C by defining it to be on an integer A. It is the previous chi if they were relatively prime and 0 if not. And Dirichlet studied a function, and this is actually Dirichlet's notation. Ls chi is a sum from 1 to infinity of chi n by n to the s. And so this is Dirichlet's L function. Functions, the study of such functions is a very important part of the Langlands program, which is a big part of modern number theory. And what Dirichlet really proved. So no, I need some more board space. So maybe I'll put down the real theorem of Dirichlet here. So continuing, if chi is a non-trivial character, non-trivial, such a function, we'll call it a character of z mod n z cross, then he proved, so the first statement is he proved that L1 chi, the value of this guy, if I put, so s is some variable, so you put the value at 1, he proved that this is not 0, and then he deduced from this that there exist infinitely many primes in the arithmetic progression take an A, then I add A plus n, A plus 2n. The kth term in the series would be A plus k minus 1 times n. So this n could have been 4, and I could take 1 plus 4, 1 plus 8, and so on. So this I'll be looking at all integers of the form 1 mod 4 or all integers of the form 3 mod 4 if I work with n equals 4. And he proved, and this has density, the set of primes in this arithmetic progression has density 1 over the number of such integers. So this is standard notation. The number of integers relatively prime to n is denoted by phi of n. This is called Eulers Phi function. Is 1 over phi of n. So what sort of statement is this? Why do people care about it? Well, what's happening is there is a certain function that he very cleverly cooked up in some very, it just came out of the blue, this thinking. And this is a function of a complex variable. It's some purely analytic property of this function is capturing some kind of deep arithmetic of amongst numbers and amongst primes and so on. So there's an entire area of mathematics now devoted to understanding these kind of things. So this value at 1 of an L function is a special value, and the subject is special values of L functions, captures a lot of arithmetic. So my own research is in this area of, there are all kinds of L functions. Instead of looking at Dirichlet characters, you can, an arbitrary L function is some series of that type for some sequence an, and this sequence an might be coming out of some other, maybe there's some geometric problem, maybe there's a Diophantine equation, and I'm looking at solutions of this Diophantine equation, mod prime powers, I can put together those things, and there is, that L function is called the Hasse-Weil zeta function. There are the Langlands program. Whatever the Langlands program is, many people consider is like some kind of big unifying theme in modern mathematics, because it just conjecturally produces a lot of bridges between seemingly disparate areas of mathematics. And the bridges, and you might have heard of Andrew Wiles's great work, or one of the few theorems which made it into the first page of New York Times, when he proved Fermat's last theorem, which was an instance of the Langlands program, that there is some bridge between the world of elliptic curves and world of modular forms, whatever these words mean. And all these bridges in the Langlands program are mitigated by some idea of these kind of functions. This world of mathematics, you can construct some functions of this type. Some other world, completely different looking world, you can construct L functions of this type, and this bridge is mitigated by an object here and object here. These two L functions are the same. Therefore, there is some relation between these objects, even though directly you cannot produce a relation. So Andrew Wiles's theorem is of that type. So these kind of, the study of these L functions form a big part of modern mathematics of that type, number theory going into Langlands program. And the principle is values of these functions at some very special points. It might look like some innocuous, like this Madhava-Leibniz series actually captures some very deep arithmetic. But juicing out this information is the hard work. There are different kinds of problems. One is simply to have some reasonable statements like this, and then to juice out arithmetic. The big names to mention are, Pierre Deline, who is also one of the few Fields medalist Abel laureates. He has this way of thinking about these kind of special values of L functions, and gives you some kind of framework of thought. What should you expect? Okay, you can look up Deline's conjecture on what are called motivic L functions. Deline's conjecture on motivic L functions. And then what sort of arithmetic is embedded? That's a different story. That's, I don't know, in this talk maybe it's kind of doesn't, I'll be just throwing words and names. So again, the take-home message, I guess, is the function that Dirichlet constructed is an early instance of an entire family of L functions, which is prevalent in modern number theory. And people try to understand the values of these L functions at various points. In this case, it boils down to, in the classical scenario, it boils down to some series like this Madhava-Leibniz series. And then one wants to juice out arithmetic information in that special value. Okay, so with that statement, I think I'll just stop. Ask me questions. Yeah. Yeah, so maybe it is. So let me just work out what happens for n equals 4, and then you will see this. Take n equals 4. So if I look at what are the possible residue classes when I divide by 4, they are captured by 0, 1, 2, 3. So what are those which are relatively prime? Well, you delete these two. These are the relatively prime to 4. And I want a homomorphism from this to complex numbers, non-zero complex numbers. The only non-trivial homomorphism, these are words, I don't know if you know such words, has to send 1 to 1, and will necessarily, if to be non-trivial, it has to send 3 to -1. And then if I apply this recipe and construct this function, so what does this function look like? Ls chi. Well, chi 1 by 1 to the s, that's just 1. The next term is chi 2 by 2 to the s, but 2 is not there. That's 0. Chi of 3 by 3 to the s, 3 is mapped to minus 1. So this becomes minus 1 by 3 to the s. Chi 4 again is 0. Chi 5 is like 1 modulo 4, so that's 1 by 5 to the s, and you see the pattern. Minus 1 by 7 to the s, plus 1 by 9 to the s, and so on. So for this particular chi, L1 chi is pi by 4. If I put s equals 1, this series becomes the Madhava-Leibniz series. So this is a special value, so that this guy is a special value of a certain Dirichlet function. So that's of course, the real meat is here. This is magical. You know, what has this series got to do with the structure of primes or the form 4k plus? So that's where, I mean, it's impossible to do that in one lecture. This is like a one semester course to understand this. Yeah.
So, in this case, there was only one possible non-trivial prime.
Yes.
If we take some other case, some other prime suppose.
Let's do it.
Different values of chi, will that give us different kind of information about?
Yeah, actually, so in the proof of Dirichlet's theorem, you will need all the non-trivial chi's. For all of them, the value at 1 should be non-zero. So some of the package of that entire information is necessary, not just for one of them. So if I take, I don't know, so you're in which year? Third year. You've done some group theory? This is a finite abelian group. I'm looking at all homomorphisms of this finite abelian group to C cross. Exercise. This is the set of homomorphisms. So take any finite abelian group. This is isomorphic to A. It's a bad isomorphism, but nevertheless there's an isomorphism. So there are as many non-trivial characters as the cardinality of A minus 1. Okay, the identity is so there can be many such, and you want to prove this. This is to be known for all of them. This is to be known for all of them. Look up Sayre's course in arithmetic, or Ireland and Rosen, whichever. Sayre is very slick. Sayre's writings in mathematics is considered, you know, the ultimate in the art of précis writing. Now I know this whole business of précis writing is lost upon the current generation. It was already getting lost upon when I was a student, and now some of your, do you even know what is précis writing? No. Yeah, look, that's and in the art of writing mathematics, you know, you have to exercise this. So what is précis writing? You have some passage. You want to keep all the essence of that passage, all the content, but kind of cut out all the noise, okay? Cut out all the unnecessary adjectives and, you know, anyway, so you might have a 100-word passage which you need to cut down to 25 words. And when you write, finally the hope is, you know, you all go on to become great scientists and mathematicians, and you'll be writing, and this is, you will need to do this. Sayre, his book Course in Arithmetic is just, you know, I don't know, 70 pages, 80 pages. It's really thin, but there is a lot of mathematics embedded there. He is considered really one of the, you know, great masters in the art of writing mathematics. Those of you who are interested, you can email me. I'll just send you something in the way of writing mathematics. There was a number theorist, David Goss, at Ohio State. He recently passed away. So he wrote a 4-page article on how to write mathematics, various things he's learned from Sayre. And you can learn many things from that. That was an extended thing to say that Ireland and Rosen's book is like 200, 300 pages, and this theorem comes, I don't know, in the 18th chapter or something like this. But it can be done very slickly also. Yeah. That's obvious. Yeah, why? Why is it obvious? They all have to be odd numbers, so it cannot end with 0, 2, 4, 6, 8. Is it? I don't know. I will leave my colleagues. Yeah.
It's a very recent theorem of Granville and Eulers
I see.
Phi.
What does the theorem say?
I don't remember the exact statement, but if a prime number ends with digit 3, the probability of the next consecutive prime number ending with 7 is higher than
I
the
see.
probability that the next digit would be 1.
Okay.
Theoretically, all of them have same chance to come. But
Yeah.
the bias toward
I see.
which one leads the other come.
Yeah, I mean, this is the beauty of number theory. I suppose one can, this statement makes sense. First of all, so let me just, for the sake of everyone, any prime is other than 2, they're all odd. So the last digit has to be 1, 3, 5, 7, 9. It cannot be 5 because then 5 is going to divide that number. So it's 1, 3, 7 or 9. And then you can start asking probabilistic questions. Set of all primes ending with 1, set of all primes ending with 3, 7 and 9. Dirichlet's theorem applied to capital N being 10 will tell you that these are equidistributed. Now, the question here seems to be, if some prime is ending with the last digit 3, what can you say about the next prime, the last digit of the next prime? And apparently there is some recent theorem which says with high probability the last digit of the next prime is something. Yeah, I really don't know this kind of, I mean, I'm not up on the literature on this, but it's very recent, yeah. I mean, the name she mentioned, Andrew Granville and Soundarajan, this is Kannan Soundarajan, he is at Stanford. Of course, as you can guess, he came out of India. Fantastic analytic number theorists of our times. These are big names in number theory. Any other questions? You will ask later. You can ask, it's okay. He wants to show off. Show off. Now you have to. Yes. Of course. The simplest example is to look at H2 of P1. And the point is, I don't tell you P1 or what, and somehow that is the motive. So you can think of this as, Theorem cohomology of P1 over complex numbers. For most of the audience, this might be just words, but you might as well hear it. Or I can look at, singular Betti cohomology of P1 of C. Or I can look at L-adic cohomology or Ital cohomology of P1 over Q. And some comparison theorem between Theorem and Betti gives me, so there is some comparison isomorphism here. And this guy, there's an action of the Galois group of Q bar over Q. And the moment there's an action of this Galois group, you can take the art in L function. And if you take the art in L function for this, you actually get the Riemann zeta function shifted by 1 or something. So there is an L function, and from this comparison pops out two numbers, C plus, if I denote this M, so Deligne constructed two numbers coming out of a comparison between the Betti and Theorem realization. And these two numbers suffice to capture the possibly transcendental part of special values of this L function. So this is the nature of Deligne's conjecture. So more generally, there is some category of motives which is cut out by cohomology of smooth projective varieties, and the basic steps are of this type. Look up Deligne's article in Corvallis volumes. This is call it a day. Okay, very good. Let's get dinner.
So we thank Professor Raghuram for this talk. Next week's talk will be on Thursday at the same time.
Thursday.
Yeah, Thursday. On algebraic geometry.